To start off here with another conservation of energy question. This is a roller coaster type problem that we're going to see a lot of times, including on your unit test coming up on Tuesday and including on your final exam. There will be one of these in both cases. And including 2 weeks from this past Monday, when we go on our field trip, we're going to see this fairly often as well, where we have to use conservation of energy for a roller coaster type problem. So here's the deal. This roller coaster cart is moving at 5 meters per second at the top of a 30-meter high hill. It goes down the hill, and then it goes back up another hill that's 12 meters high. My question is, how fast is this roller coaster moving at the top of the second hill, the 12-meter high hill? Notice there's one thing conspicuously absent from this. What is it? The mass. Do we need the mass? What have we come to notice over the past several questions that we've done involving conservation of energy? The mass cancels. As long as you're dealing with just kinetic and just potential, that's going to happen every time. If you have something like elastic potential, then that doesn't happen because there's no mass appearing in that equation. But we don't have to worry about that yet. Okay, for now, gravitational potential, kinetic energy, the mass will cancel. So it turns out we don't even need one. If you're not comfortable with that, make up a mass. Okay, as long as it appears in every term, it's going to work out for you. All right, we'll give you a few minutes to work on that question, and then we'll take a look at it when you're finished. Let's have a look at the question here. So here's our roller coaster, top of a 30-meter high hill. How is it moving, or how fast is it moving, sorry, at the end of a hill that's 12 meters high? What kind of energy do we have at the beginning of this problem? Does it have a height? Yeah, it does. So it's got potential energy, right? What kind of, does it have, is it moving? Yeah, so it's got kinetic energy as well. Ah, man, yeah, the subscript's all wrong here. What about at the, oh, wait a second here. I was going to say, what about at the end of this problem? But I got something in between here, right? Do I have to do EI equals EF for this and then do it for this? How many people said mgh plus 1/2 mv squared equals 1/2 mvf squared, solving for this speed, and then turned around and said 1/2 mv squared equals mgh plus 1/2 mv squared for this one? So how many people did it? This is problem 1, and this is problem 2. Hands up if you did that. Okay. What'd you get for an answer? 19.4? Who else did that? What'd you get for an answer? Sorry? Okay. Okay. 19.4. So you guys are getting the same answer. That's probably the answer then. Anybody else do something different? Taylor, what'd you do? Yeah, you know what? That's what I did. That's what I would do for this question as well. If we call this position 1, position 2, and position 3, we know the energy at 1 is equal to the energy at 2, right? And we know the energy at 2 is equal to the energy at 3. Well, what does it tell us about the energy at 1 and 3? They're equal. So I can say easily E1 is equal to E3, or EI is equal to F, this being my initial point and this being my final point. So I'm going to say that my final energy is over here, and it's 1/2 mv squared plus mgh. Cancel out the masses. By the way, if you do it the way that some of you did it and solves it as two problems, position 1 equals position 2 equals position 3, that's right. Right? We know that the energy at any 2 points along that path is the same. So that's absolutely correct. It's just a little bit more work, that's all. What do we got here? 9.81 times an initial height of 30 meters times, or plus 1/2 times 5.0 squared equals 1/2 of VF squared plus 9.81 times 12 meters. 9.81 times 30 is 294.3 plus 12.5. What's 12 times 9.81? 117.72. All right, let's, what do we got here on the left side? 306.8. Let's take the 117.72 over by subtracting. What do you get when you do that? What is it? 189.08 equals 1/2 VF squared. And we know we can get rid of the half by either multiplying by 2 or dividing by a half. That's either way is correct. Square root that, and we end up getting, what was it, 19.4 meters per second? Sorry? No, yeah, I guess it would be 2 digits. Yeah, you're right. 19 meters per second. I don't really care which way you do it. I don't really care whether you do it position 1 equals position 2 equals position 3, or just position 1 equals position 3. I don't really care. Okay, but in the end, if you want to save yourself a little bit of time and effort, understand that you don't need to do all the middle steps. I remember once I put a question on a final exam, and I don't think this one's on your final exam. I think I've replaced it since then. But the question was something like this. And we were given the initial speed up here and the initial height. We were given all the heights of these hills. And we wanted to find the speed of the car over here. And some people did E1 equals E2, E2 equals E3, E3 equals E4, E4 equals E5, 5 equals 6, 6 equals 7, 7 equals 8, and 8 equals 9. That is a lot of work, as opposed to saying E1 equals E9. Okay, so it's correct, although you start doing that many problems with it, you're bound to make a silly mistake somewhere, right? And that's what most people that did it that way did. They had the right idea, but make a silly mistake there. You do this way, E1 equals E9, EI equals EF, and you're much less likely to make a silly mistake. Okay, one more of these, and then we're going to move on to our new unit, actually. This time we've got a situation where we've got a roller coaster similar to one that I was on once in Las Vegas. It's not there anymore. It's been gone since you guys are old enough to remember. Even if you've been to Las Vegas, you wouldn't have seen this one. It was a really neat roller coaster, though. It was really, really short, but started off in this cart actually inside a restaurant, indoors inside a restaurant, and then they used this electromagnetic propulsion system to propel you forward from 0 to whatever speed it was. Okay, let's say 25 meters per second. Okay, I don't know exactly how fast it was. Like almost instantly, like your head's back against the headrest, like crazy, because the G forces you're pulling as you're accelerating are crazy. And then you go around this turn, and then you go down this little hill, and then you go around this upside down loop, and then you go straight up this track. So it looks something like this. You're starting at a speed of, let's say, 20 meters per second here. You're not really starting at 20, but as soon as you're moving at 20 meters per second. You go down this little hill like this. Then you go around this vertical loop like this. That has a radius of, let's make the radius 10 meters here. And then you go up this hill like this, straight up, and then the track ends. Like there's just no track. So you're going up, you're going on this roller coaster cart right here. You're going down, down, down. You're going around this loop, and then you start slowing down as you see the end of the track coming, and as you know, your mind is telling you that you're going to stop before you get to the end of this track. But still, somewhere your body is thinking, uh-oh. But then you stop, miraculously stop, just in time, so that you don't go off the end of the track. And then what happens? You drop, and you go through the whole thing backwards. Um, the question is, my question is, how high do we get up there if this is, let's say, 8.0 meters from here? Okay, let's see what you can do with that one, please. Time to take a look at this. Um, we got a bunch of things going on here, right? We start at a little hill here, 8 meters high. It goes down that hill, goes around this loop, which honestly is completely irrelevant, right? In this question, at least, it's completely irrelevant. Back down here, and then back straight up this last incline there. We're going to make this our initial point, and way over here our final point. What happens in between is irrelevant to us. So we're going to say, what do we got at the beginning here? Well, Emma, is it moving here at the beginning? So what kind of energy do we have there? Kinetic energy, 1/2 mv squared. Shay, does it have a height there at the beginning? Yeah, so it's got potential energy as well. mgh, initial. Now let's fast forward towards the end of the problem. Julia, does it have a height at the end of the problem? Yeah, it has a height, so it's got potential energy at the end of the problem. Is it moving at the end of the problem, Bruce? No, no. So the kinetic energy would be 0 there. We have 3 terms here. Mass appears in every term, so we'll cross that off. We don't have to have the same number of terms on both sides. We just have to have the mass in every term on both sides. So let's say VI, what do we got? 20 meters per second. Don't forget to square that. Plus 9.81 times the initial height is 8 meters equals 9.81 times the final height. So we're going to say 20 squared times a half, I believe, is 200. 9.81 times 8 would be 78.48. Thank you. Now it's getting easier here, right? 278.48 divided by 9.81. And what do we end up getting for that? About 28 meters per second, 29? Sorry. Yeah, sorry, that's a height, right? Boy, you better not be moving at 28 meters per second when you get to the end of that. Okay, the height is 20, what do we say, 28 or 29, did we say? 28.4 or 28 meters. See, and I'm going 28 meters into the air. Make sense? Good? All right.